All right, we'll go ahead and get started. Thanks for joining today. So this webinar is on optimizing play for production. I'm James Ward from Typesafe. And today we're going to go over some things that we're going to assume that you have some knowledge of play. I'm going to start with a little bit of the basics, but then we'll dive right into talking about some of the performance pitfalls that you may have with your play applications, talk about some troubleshooting tools, talk about thread pool configuration, and then talk about front-end servers and load balancers. And then we'll wrap up talking about static assets and how to have better performance with those. So that's the agenda. If you have any questions or problems throughout, then enter those into the questions pod in the webinar, and we'll have a Q&A at the end, so we can go through any questions that you've entered throughout. If you're having any problems, then we'll have somebody help you with those while we're going through the presentation. So with that, let's dive in. So I'm going to be using a tool called ACTIVATOR. This is a new tool that Typesafe has created to help you build play applications and Typesafe platform applications. And you can get that, of course, on typesafe.com. This is really a drop-in replacement for the play command. So if you, many of you are probably play users already, you can use the play command like you've been doing, or you can use the new activator command. So both of them are essentially just SBT. So with that, let's actually go create a new application that we'll be using throughout this presentation. So to do that, I'm going to run activator, and I'm going to say activator new. There's also a UI for Activator. You can launch that either by double-clicking on the Activator launch script or by running Activator UI. I'm just going to use the command line today. So I'm going to create a new application. We'll call it Hello Play. And then I'm going to create an application from a template. There's a bunch of different templates you can choose from. I'm going to choose the Hello Play template. So now my application is created, and I can go into the Hello Play directory, and this is my application. So this is just our standard play application, and now I can run the application. I can and do all the other commands on it that we'll be going through. So let's actually run it. First thing I want to show you is the different ways to run in development mode. This will be important because there is a distinction between development mode and production mode. So if we just do activator run or play run, this will run the application in development mode. So this will be up and running in a second, and then we'll be able to browse to that application, this play application, and load it in our browser. So it'll resolve the dependencies there, and now we're up and running. Let's go to localhost 9000. This will cause the application to compile. And then one of the important differences that I want to show you between there's actually two different ways to run the application. So there's play run and there's play twiddle run. And these actually have different behavior. We'll see it actually live in a second, but to explain it, play run, what it does is it waits until you hit refresh in the browser, and then it checks to see if anything needs to be recompiled, and then if so, it'll recompile it, and then the request will then be using the new recompiled version of your files. Twiddle run, on the other hand, works a bit differently, and let me show you. Let's actually run in that one. Twiddle run is what I usually use when I'm working on play applications. The difference with twiddle run is that it will twiddle run will watch the file system for changes, and now rather than waiting until I hit refresh in my browser, it will instead be sorry, one sec, making sure that everything's okay with the webinar. Okay, so instead of waiting until you hit refresh in the browser, it will watch the file system, and whenever the file system changes, then it will recompile. So this just gives us a few extra milliseconds faster. Usually by the time we get to our browser and hit refresh, then everything will automatically be recompiled. So here's our little play application. I'm going to open it up in IntelliJ so we can write some code. So in the newest version of IntelliJ 13, you can actually just go open this project directly. We don't need to generate the project files, which is a pretty cool new feature here. So I'm going to go find this thing on my desktop. There it is, Hello Play, and then I'm going to select the build.sbt file. That's our build definition file, and I'm just going to import this project now right into IntelliJ. So it'll take a second to resolve those dependencies and then open up. So while it's opening up, let's go talk about the other ways that we can run a play application. So play run is, or activator run is what we use when we're in development mode. if we want to run in production mode, instead of doing run, we can do start. And when we do start, the difference between run and start is that start will run now in production mode. The primary difference between development mode and production mode is that in production mode, we won't do that check to make sure that everything needs to be, or check to see what needs to be compiled. So play start, if you're going to do a local load test, then you'll want to use the start task there instead of the run task, because there's definitely a lot of overhead on every request for checking to see if anything is new and needs to be recompiled. So you can do that from the command line. So that's great. We can run in production mode through that way, but there's a few other ways to run in production mode, and these are more oriented around how we actually get to production. So a lot of times if we want to test a production bundle before we actually do a deployment, the way to do that is with the stage task. And so let me just show you that one real quick, how that works. So exit back out here, and we'll go to Activator, and then we'll do a stage. And Activator stage, what this will do is compile the application and then bundle it up into something that I could copy onto a server and use. So it'll do all the compiling, do all the bundling, and then stage will put the files into the target directory, and then there's a universal directory in there, and then there's a stage directory, and now this is all the files that I need on my production server to run this application. So you see there's a bin directory there and a script that I could start this application up now in production mode locally. So stage is a good way to test that when you are going to take this thing into production, that it's going to work as you expected. And there's one other command here, which is Dist, and play Dist does essentially the same thing as stage, but then it will assemble everything into a zip file. So there we go, we get our zip file now, which is essentially just everything in that stage directory. So a lot of times we'll use this zip file and copy it onto a server or servers, and then we have everything that we need to run our application in production. So that's the basics of how we create a distribution. Most CI servers will do either a dist or possibly a publish as well, or an alternative to zip would be to do a publish. The difference between a dist and a publish is that the dist has everything that we need to run this application on a production server, but in some production configurations, all you really need is the library, which is for the application. So see in here, in this stage lib directory, here's this default.helloplay 1.0 snapshot.jar. This is actually my application. This is what my application needs, what my application has custom in it. Everything else in here is just all the dependencies that my application has. And so in a lot of production configurations, we'll just take this jar file, we'll publish it to like an Artifactory server, and then our production servers will pull this jar file out of those Artifactory or some repository and put it on the production server. So that would be using the publish tasks via Activator, SPT, or play. All the same thing. Okay, so let's go back here and let's go rerun this thing with twiddle run. So now that you know how to create a production deployment of this application, let me show you a little bit further information on the differences here between the development mode and the production mode. So this is my application here in IntelliJ. I have this main controller.java file, and this is my Java source code that is my controller that's handling this request. So see there's a message here, hello from Java. If I go in and change this, say hi, file will automatically compile. So it's because I'm using the run there. So now when I go back and hit refresh in my browser, then we see that, all right, everything's been recompiled, and now my request gets to the new version of that file. Also in development mode, Play has a nice way to display compile errors. So if we hit refresh in our browser and we have a compile error, then we'll see that compile error right in the browser. And so that gives us a nice way to see those errors. Of course, we will, if we're using a IDE, then we should be seeing those errors in the IDE as well. But we can go back. Looks like everything's good. Okay, so that's how the differences between development and production mode. So now let's dive into a little bit further about some of the performance pitfalls. So the first one that I want to talk about is web tier state. Play is a stateless web framework by default. This allows us to scale horizontally so that we can just add new Play servers behind a load balancer, and then these Play servers without any state. It doesn't matter where a request goes. It doesn't matter which server actually handles the request. It's all going to work just fine. And so this is very different than a typical stateful web framework. If you're familiar with like JSF or a number of the older legacy Java frameworks, those are stateful web frameworks. And so what this means is that now we have to have some way to hold our state, and our load balancer has to always send requests back to the same server that has the state, and then to handle failover in case that server dies, we have to replicate that state across servers, and this is really a painful way to scale. So by being stateless by default, Play is able to scale horizontally a lot better. You certainly can do things in your application that would make it not stateless. So we try to make that out of the box with Play a bit difficult to do. So there is a session object you can use in a Play application, but the session object actually stores inside of cookies rather than inside of something in the server. So there is a very limited amount of data that you can put into that session. There is a pretty typical way that we do put state on our Play servers, and this is through an in-memory cache. So you can always use an in-memory cache. The thing about an in-memory cache is that you have to make sure, if you're in a multi-server environment, that you are replicating that cache across the server. So the easiest way to do that is actually just to use a plugin for the Play cache system to move that cache outside of memory and back into an external data store, so that all of your web applications would be talking to a cache that's always consistent for them. So then your web server tier would again become stateless because we'd be moving that cache out into an external system. So that's really the recommended approach with Play, is to keep the web tier stateless. If you're in a single server environment and don't care if the cache goes away when the server restarts, then sure, you can use the in-memory cache just fine. So the nice thing about this architecture is that it fits really well with the RESTful way that we're building applications now. REST, pretty much by definition, is supposed to be stateless, and so Play fits very well with the RESTful way of building applications. It also fits very well with the new style of moving the UI to the client side with JavaScript. So frameworks like Angular and Knockout and Backbone work very well with Play, because we take all the state that we used to have to store in memory in the web tier, and we actually move that all the way down to the client side. And so this makes it so any request to the server, it becomes a stateless request to just get some data, serialize some data, perform some operation on some data. So Play fits very well in these cases, but you certainly can add state into your web tier and make it a lot harder to scale your application. We would definitely recommend against that. So another often encountered performance pitfall is unnecessary serialization. So a lot of times in our applications now, a lot of what they're doing is just taking data from one place, changing that data, and then putting the data back out to the end user. And so there's a really nice way with Play and the Scala JSON library to do what we call JSON coast to coast. And JSON coast to coast allows us to avoid this unnecessary serialization and deserialization of data. If we're talking to a backend data source, whether that's a web service or a Mongo database or some other JSON-based data store, and we're going to give the client JSON, so we're going to expose JSON to the client, there's actually there can be no reason to actually do a transformation of that data into in-memory objects and then convert those objects back into JSON. It results in a lot of overhead that may not be necessary. So in the JSON coast-to-coast model, we actually have an API to do transformation of JSON data. So if I have a JSON object and I want to apply a transformer to that object, then I can do that very easily through the Scala JSON API. We don't have something similar for the Play Java JSON library, which is just Jackson, but I'm sure there are some Java libraries out there that'll do similar things. So there's all sorts of different things that you can do in these transformations. You can combine data, you can take fields out of the data. So this is really a great way to save on the overhead of serialization that may not be necessary. So if you want to see some examples of that, if you just go to the play documentation, there's an article, or a JSON transformers doc in the play documentation for that. So the next one, and probably the biggest performance pitfall that is by far the most common place where we see bottlenecks in play applications, it comes down to blocking. Blocking is when we have a thread or something that's going to process some action, and when we're not actually using that thread, we still hold on to that resource. That's traditionally what blocking is doing. It's just holding on to resources that don't need to be held on to when they're idle. So a very common example of this is that anytime we make a request to a database, there's some amount of time where we're just waiting on the database to give us a response. And in the typical model, when we're doing this, we're actually holding on to these precious threads while we're waiting for the other side to respond. And this can be true for databases. It can be true for talking to web services. So lots of different ways that we can block. So the reason why this is a problem is because we really want to keep our thread numbers as small as possible down to the number of CPUs that we have. The reason for this is that there becomes a lot of contention between threads, and we lose the ability for our CPU caches to be taken advantage of, and threads do have a fairly significant memory overhead per thread. So we really want to try to reduce the number of threads that we're using as much as possible. So by default, play is set up to be non-blocking. It's set up to not block threads. And we in play do this down actually at the way low level underlying networking connection. We actually do it at the 8K byte chunk level. We can do non-blocking. And so this means that we're not going to block a thread unless we're actively transferring an 8K byte chunk of data. So, so I want to give you an actual real example of this. The typical way that we would deal with a request that comes into our server and then a request that then goes out to some other service is that we would be potentially blocking two different threads, and these threads would be blocked even when we're just waiting on the other side to respond. This gets really expensive when we want to do things in parallel, which is now a lot more common. Now our web applications are consuming resources from a bunch of different places. We may be making 20 different requests in our backend just to handle one incoming web request. So really the model that we'd like to get to is where we don't block these threads when they're not actively being used. So let me dive into some code here and actually show you an example of what this looks like. So I'm going to go create a new controller here in my play application. So we're going to give it a route of /foo, and this is going to go to my message controller and a foo method that I'm going to define there. I'm going to be using Scala for this, but certainly everything I'm showing could be done in Java as well. Just a little bit less verbose to write the code here in Scala. Okay, so let's define this method. So my foo, it is an action. An action in play is really just something that takes a request and returns a response. So my default action, I can just say, let's return OK, which is a status code 200, and let's make it say ASDF in the response body. So let's go try that out. Let's go to /foo, and this will compile, and then we should see that ASDF there right there in the browser. So great. So everything is good now for handling this request, and actually underneath the covers, play is actually implementing this request in an async and non-blocking way. So everything, all of the request handling in play underneath the covers is implemented in an async and non-blocking way. But my code, the actual thing that's producing this response, this is a blocking call here. It's not blocking for very long. It doesn't take very long to assemble this result, but the amount of time that it does take to do it, it is blocking. And so, so play by default, our actions are just assume that we're going to do something blocking. But there's an easy way to turn this action into something that will be non-blocking, and this is by using the action.async. Action.async is a way now to not return the actual result, but return a handle to something that will produce the result in the future. And of course, you can also do this from the Java API in Play as well. And there's good docs on that in the Play documentation. So now I can't just return a result. I need to return something that will return the result in the future. And so this is what we call a future. And I'm going to import this. And then let's do future.successful. Future.successful just creates a future that will hold this result and produce this result as soon as we need it. And so as soon as Play can get a thread and handle this request, then the future will fulfill with this result, which will just be the same thing. Actually, let's change that so we can see something different. So now when we hit refresh in the browser, it'll recompile, and then there we see our foo. So in this case, now we are async. We're still not non-blocking, at least in my code, because I don't have anything to not block on. So in order to be non-blocking, we have to have something to not block on. And this is really what we would like for all of our code that can be non-blocking, is to be non-blocking. If we don't have anything to not block on, then you don't have to add this extra boilerplate. You can just do what we started with. So an example of someplace that we can't be non-blocking is with templates. So if I have a server-side template, like in here, this is a server-side template, there's no way to not block on this server-side template returning a string essentially out in the HTTP response. So there's just no reason to add the extra boilerplate there. But let's create something that we can be non-blocking on. An easy one is just to do a timeout. So if I do a promise.timeout, let's import the right one here. There. It's this one is the one we want. Promise.timeout. What this will do is after the given amount of time, it'll produce this result. So let's give it our OK and as the result to produce there. And then this takes a second parameter, which is how long we're going to wait to produce this result. And let's do 10 seconds. In order for this to work, I do need to import my duration stuff. So let's go into the Scala concurrent and import duration dot underscore. Just means everything in that package. Okay, so promise.timeout, what it actually returns, if you look at the signature there, it returns a future of A. A is, in this case, a result because that's what's there. That's what's defining my A. We'll also see on this promise.timeout that there's a second parameter set that we need to specify here. We've got the first parameter set, which is a message and a duration. Then we need to give this thing a third parameter, which is the execution context. Now that we're doing something asynchronous, we're going to be using another thread, and so we need to tell this application where to get its thread from. And we have an abstraction on top of threads called execution context. And these are the way that we actually tell this how it's going to get a thread. So we could explicitly set the execution context here. Instead, I'm going to do it differently. I'm going to go to the import execution context, and I'm going to get the implicits global. If you're not familiar with Scala, all that this is really doing is because I've imported this, it's going to now fill in that third parameter with this default execution context. The default execution context in Scala just has like 1 plus the number of CPUs as number of threads in the execution context, and it uses a fork join pool. We can, of course, create our own execution context, and this is really a good way to optimize our performance, is that when we talk more about how to deal with blocking, one of the ways that we do this is we create an execution context for our blocking stuff, and then we can allocate a lot more threads to that execution context. So we'll talk more about that in a little bit. But let's go try out this application and make sure it works still. Let's change it here to say, let's go back to ASDF, and so we can see that now we're making a request. We'll see that my browser is just spinning because I told it to wait for 10 seconds before it returns a response, and then after 10 seconds we see our ASDF. So if we go up and go into the inspect element here and reload this, we'll see spinning for 10 seconds, and then it will return that response. So now here's the really cool thing. Now we have something to not block on, and so for that 10 seconds that my application is just waiting, there's actually not a thread allocated to that request handler. So this means I could have thousands of people all waiting in this wait state, and I wouldn't have to have any additional threads to handle those requests. If I didn't have this, async and non-blocking context, and I had 1,000 people all in this waiting state, then I would need 1,000 threads, and that becomes very expensive in terms of the JVM context switching overhead and the memory overhead to doing that. So this is definitely the preferred approach for how we can scale much better, is to be non-blocking. So let's now switch gears to a little bit more practical example. Promise.timeout is a simple case, but probably not one that we would be using in our production applications. So one that we would be using in our production applications is, let's say that a request comes into this foo controller, and now I'm going to make a call to another web service, get some data from that web service, and then do something to it and return it. So as just a real simple example, let's create a new request handler, which is going to use the Play Web Service Client library, which is a reactive. It's async and non-blocking library for doing web requests. And I'm going to use it to make a request to jamesward.com. That's my blog. And I'll make a GET request. So a GET request, if we look at the method definition here, it returns a future of a response. So this is something that will, in the future, have this response in it. And so this allows us to be async and non-blocking with this request to jamesward.com. But there's one thing I need to do with this, is that I'm getting back a future of a response, and if we look at the method definition for action.async, it takes a future of a result. So I need to transform that response into a result when I get that response back. So the easy way to do this is to do a map, and a map says when we get the response, then take that response and produce a result, or turn it into a result. So now I'm going to do OK, and I'm going to take my response.body, which is just a string, and I'm going to return that in the status code 200 response. So now what this map actually produces is a future of S, and S is this thing, which is a result. So this jwf.map, that produces the future of the result. And now we are async and non-blocking. So let's go try it out here in the browser. So there we go. There's my blog, jamesward.com, and you'll see that it's just text because I gave that OK method a string. It didn't set the content type, or just set it to text plain. I could, of course, set the content type to be the right text HTML content type. Okay, so now here's a cool thing. Let's go hit reload again. So there's some amount of time here where you see my browser spinning. There's some amount of time where the request coming into my server, and then there's a request going from my server to my local server to jamesward.com. There's some amount of time where I have two requests, and both of those are just waiting on jamesward.com to respond. So in that time, Play actually can take the threads that were allocated to those requests and give them to somebody else. And so this really allows us to scale a whole lot better, because now we're not just holding on to these resources when they're not actually being used. So this works the same way as being synchronous, in terms of I'm just returning a response, but now I'm async and non-blocking. The Play Web Service Client library is really just async and non-blocking. If you want to make it blocking, which we wouldn't recommend, but if you wanted to, you could do what's called an await.result and just block until we get the future fulfilled, until that value comes back. But that's not the recommended approach. The recommended approach is to be async and non-blocking all the way through your controller code. Okay, so that's our quick little intro here to async and non-blocking requests. Let's take this one step further before we move on, and this is what's called reactive composition. With reactive composition, let's say I have two requests here, and one to jamesward.com and one to twitter.com, and I want to be async and non-blocking for both of these requests, and I want them both to run in parallel if possible as well, if I have enough threads to do that. So there's a really nice syntax in Scala for being able to compose together these results. What I'm going to do is I'm going to use a for comprehension. I'm going to say, let's get the JW response out of the JW future. Let's get the Twitter response out of the Twitter future. And then once both of these responses have come back, let's yield. And this is where we're going to return our are okay. And let's take the Twitter body and let's just add that to the JW body. Obviously, in the real world, I'd be working with JSON data instead of these giant text blobs. But there we go. Now this for comprehension returns a future of a result, and that future of the result will be completed. Will have its value as soon as I get the values out of both of these requests. So let's go give this a try and just make sure that this composition works. And there we go. So now there's some amount of time where I have 3 requests. I have the request from the client to the server, the request from the server to jamesward.com, and the request from server to Twitter. And there's some point in time where all 3 of those requests are not using any threads because we're just waiting on the other sides to respond. So that's reactive composition. Okay, so that's really the preferred approach, is to be non-blocking. This is the best way to scale. It's probably the biggest performance bottleneck that you'll have in your application is when you're blocking. And so non-blocking is better. Play's web service client library is non-blocking, and then there's some data store libraries for Play that you can use that are also non-blocking. So things like reactive Mongo, there's a Redis driver, there's a driver for Datomic. So a lot of the newer NoSQL types of backend data stores now support non-blocking drivers. So this is great. It can allow us to scale our applications and use threads much more efficiently. Now, the one caveat to this is that a lot of APIs that we still have and use are blocking. So things like JDBC, the HTTP client from Apache Comments, there are a lot of APIs that we are likely using that are blocking. And so there's, in a lot of cases, there's no way to avoid blocking. We have to block. And so there is a easy way to deal with this type of blocking, which is just to throw threads at it. If we have things that are blocking, then we can allocate more threads, and up to some amount of some point, depending on how much memory we have available, or depending on how much CPU thread contention we're able to deal with, and GC contention, those sorts of things. So there definitely are limits to this, but we can throw threads at it. But the problem with this is that threads can only really accommodate spikes. They can't deal with, if I have 300 requests coming in per second and I can only make 30 requests a second to my database, and I'm always at 300 requests to my web tier, then I'm never going to be able to allocate enough threads. So if at one time I have 5 requests per second, and then I spike to 300 requests per second, and then I come back to 5 requests per second, adding more threads can help me deal with those spikes. But there's no magic here. As many requests are coming in, is dependent on how many requests I can make back to my database. And threads just give us a place to basically say, hey, don't go away yet. I will in the future, once this spike goes away, I will be able to handle your request. So that's one way to deal with it. Another way is to do more push. A lot of our applications block because they need to get data, and they're maybe pulling for that data, or they're constantly asking, can I have this data, can I have this data, can I have this data? And that's just wasting a lot of resources. So if we go to push, then we can deal with this a lot more easily. So push can be done through WebSockets in Play, it can be done through server-side events, Comet. There's a number of different channels that you can use. And of course, it's all done in Play in an async and non-blocking way. So now this means that instead of blocking all these threads to pull for data, I can just push it when I have it. So then the other thing that I want to go into about how to deal with blocking is to use actors. Play and the Typesafe platform has a library called Akka, which is an actor-based model that gives us a really nice way to isolate this blocking and deal with it in a nice way. So the way that actors work are, there's an actor system and there's an actor, and what we do is we're going to send a message to an actor. What the actor system does is it actually takes that message and puts it into a mailbox. And then as soon as the actor is available to process the message, then we can send the message on to the actor. The actor will process the message, and as soon as it's done processing the message, then it is really just memory on the Java heap. So it's not using, an actor doesn't use any threads when it's not actively processing a message. Actors can also only process one message at a time. This provides a really nice way for us to isolate things that we used to have to do through synchronized blocks in our Java code provides us a really nice way to deal with mutable state in the application. And so actors provide a really great model to have an event-driven system that manages our concurrency for us. And these actors, they usually don't have a lifecycle based on a request. So this allows us to have these actors that have a totally different lifecycle than a request does. And that lifecycle can be much shorter than a request. It can also be much longer than a request. It can be the full duration of the time that an application is living. And then I'm not going to go into much detail today, but actors also allow us to isolate failure through a supervision model. So let's take this application that we've been working on here, and let's now add an actor into this application. So I'm going to come in and first create a new actor, and of course you can do this with Java or with Scala. I'm going to do it with Scala. So I'm going to create a new actor. We'll call it the James Ward actor, and this will extend the based actor class from Akka. So let's import that. And now an actor, all that an actor can do inside of the actor implementation is receive a message. So let's add a receive handler here. So now I'm going to receive a message, and in this case, the message that I'm going to receive is a request to fetch some data from jamesward.com. So it's best that we create some objects to hold these messages in or represent these messages. So I'm going to create what's called a case object here called fetch, and this fetch is going to be the thing that my actor is going to handle, the message that I'm going to handle. So I'm going to say, in the case that I get a fetch message, now what we want to do with this, when we get this message, is go to jamesward.com and fetch it. So let's just copy and paste that in there. We'll import it. We also are going to need our execution context here. So let's import that. Okay, so that's great, but now I'm telling this actor, go make this request to jamesward.com, but now I need to do something with the response. And actors can only send and receive messages, so what we're going to do is once we have this result from jamesward.com, I'm going to send that result to the person that asked for it. So to do that, I'm going to use something in Akka called a pipe because we're doing something asynchronously in this case. So I'm going to import the pipe here, and then I'm going to say, all right, when we get this result back, pipe it to the sender. So this will say, all right, when this feature is completed with the response from jamesward.com, now just send that message on back to the sender, the person who sent this fetch message. Okay, so that's my little actor. Now let's go back to my controller and let's replace this implementation here with instead now using the actor. So to do this, I first need to create an instance of my actor, and this instance could be created in a lot of different ways. I could create many instances. In this case, I'm just going to create one instance. So I'm going to create a lazy val here. We'll call this the JW actor, and I'm going to use the Akka .system .actor of. And then I need to tell it to create me an actor of, use this props and say create me an actor of James Ward. And let's import props here. So this will create what's the actual type definition of this is an actor ref. The reason why we use actor refs instead of the actual actors is because we don't want to actually hold on to this actor. This actor could be somewhere else on the network. It could actually be an actor that's been restarted. And so in order to have the resiliency and location transparency in actors, we always work with actors through the references. Okay, now we also, now that we have our JW actor, what I'm going to do is I'm going to send this actor a message, but then I'm going to wait until I get a response back from it. So to do this with Akka, we're going to import the pattern.ask, and ask allows me to say, all right, JW actor, let's put this in parentheses here, I'm going to send a message which is going to be that fetch message. There, and then I'm going to I'm doing an ask instead of a tell, and the difference between an ask and a tell is that I'm going to tell it fetch, but then I'm going to get a future of the something back. And so I've got this future of something back, and so now what I need to do is I need to map it, basically say when I get this message back from this JW actor, what I'm going to do is I'm going to say if this message is a response, because remember back in my actor, I'm taking the response and just sending that response to the sender, which is here. And so let's import that one there. And now I'm going to say, all right, when I get a response message back from this actor, now what I want to do is return my response, which is going to be the response.body. Okay. So now I've just taken what I was doing in here in futures and I've moved it into an actor. Let's go make sure that this is working. Oh, and there's one other thing we need to do, which Play will nicely tell us we need to do, but we need to import a couple other things for this to work. So first we're going to import the application the current application. We need that in order to create the actor system. So I'll just copy and paste that. And then I need to import one other thing, or create one other thing, which is when we do an ask, it always has a timeout. We need to provide a timeout. And so I'm going to create an implicit val, which is going to be my timeout. And this is going to be a new timeout. And let's import that one, and let's just tell it its timeout is 5 seconds. Okay, so let's go try this again. And now we're going to be using the actor. So the request is going to come in. We're going to then send a message to the actor. The actor is going to now, in an async and non-blocking way, be able to go fetch jamesward.com. When it gets a response back, it's going to respond with another message back to whoever asked with the actual response, and then I transform that response into the result that I need there. And so now this whole thing is async and non-blocking. But we were talking about blocking, so I picked the web service client library here, which is non-blocking, but this would also be a great way to make requests to our database. So remember how I said that actors can only process one message at a time. So I only have one instance of my actor here. So that means that I can only one at a time make a request to jamesward.com. If I wanted to be able to make multiple requests at a time, then I would create multiple instances of my actor. Okay. So that's our quick little intro to Akka. So with that in mind, I want to show you one of the patterns that we typically use, where if I have a number of requests coming in for the same resource, and it's going to take a bit of time to go fetch this resource, then what I can do based on the code I just showed you with Akka is I can say, all right, I'm going to maintain through another actor, I'm going to maintain a list of all the people who are interested in this response, and then I'm only going to have one actor actually fetching that data, and then as soon as I get the response back from that actor, then I can send the response back to everyone that was interested in seeing that data. So that's a really great way to deal with blocking, because now if we've got a number of people constantly making this request for the same data, then we can actually only make that request once and be able to have a nice programming model for how we then can scale the different parts of that. And then there's a number of other routers, we call them in Akka, that could allow us to do different routing mechanisms. So let's say we want to do a scatter gather. So let's say we have a cache system and we have the backend data store. We can actually send messages to both actors and say, whoever completes first, so whether the cache comes back first or whether the backend data store comes back first, pick that one and then use that response. Also, we can use a smallest mailbox router, so we can have a bunch of actors that are all making these requests, and we can say, send this message to whoever has the smallest mailbox, or we can do round robin, random routing. So all sorts of different routers that we can apply to be able to manage the concurrency of how these requests are being handled. So that's really some of the best strategies we can do to deal with blocking, is to put things into actors, isolate them, use different routing strategies for not tying up all the resources that we would normally have to tie up. So one of the challenging things about these type of asynchronous and non-blocking applications is that they can be difficult to troubleshoot. Where am I blocking threads? Where are these messages going? How long are they in the mailbox? So there's some great tools that help us to identify these sorts of bottlenecks. The Typesafe console is a great one. It's integrated right into ACTIVATOR now, so it makes it easy to just go in, run the console right on an ACTIVATOR project and see exactly what's going on with your actor systems and your Play application. Then there's a lot of production monitoring tools. AppDynamics and New Relic have great support for play applications. There's all the typical JVM tools, and then there's load testing tools like Gatling and JMeter as well. So lots of different tools to help us identify where the bottlenecks are. So let's talk about thread pool configuration. So we have a lot of different things that we can tweak in the JVM for thread pools. So let's talk a little bit about the different thread pools that Play has. So there's 5 different thread pools out of the box with Play. We have the Netty thread pool, which is the thing that's actually terminating the HTTP request. We have an internal Iteratee thread pool, which is being used by Play to process the response bodies, the request bodies and response bodies. We have a Play internal thread pool, which is just used for some of the internals of Play. And then we have the Play default thread pool. And this is the one that your code actually executes in. So anytime you have a request that comes in, and then inside of that action, it actually goes into this default thread pool. So there's just one of those default thread pools by default. It's the number of CPUs is the number of threads in the thread pool, and it uses fork join. And so there's just one, and you can create your own. So as I mentioned before, one of the ways that we really optimize our applications is to actually create different thread pools. We can create a thread pool that's really optimized for blocking operations and give that thing a bunch of threads, and then we can keep the default thread pool, the one that's dealing with non-blocking things, we can keep that thread pool much smaller. And this allows the JVM to much more easily optimize what runs when actually on different threads. So that's why we would split out our application into those actors, is that it's very easy to give an actor a specific thread pool that it would run on. And then there's also an internal or a Akka thread pool within Play that gets used for the Akka actor system that I showed you. So configuring the thread pools is done declaratively just in your application.conf. You can go in and set the configuration to tell it how many threads you want. So there's some different knobs you can tweak. You can change the executor from fork join if you wanted to. You can set the parallelism factor, which is the default number of threads. One means the parallelism factor is the number of CPUs that you have, and then you can set the min and the max. In this case, if I was doing had a thread pool for blocking operations, or let's say most of my application is blocking, then I would just say, all right, let's just allocate a maximum number of threads to be 300 for this application. And so then that means that I can have 300 blocked threads at a time, which means that if every request blocks one thread, then that means I could have 300 concurrent connections to my application. So there's a lot of other information in the Play documentation for how to tune the thread pools, how to create new thread pools, and those sorts of things with execution contexts. So let's talk for a minute about front-end servers and load balancers. The easiest way to terminate your HTTP connections with a Play application is just using IP tables. You basically just say, I'm going to run Play on, let's say, port 9000, and what I need to be listening on is port 80, and so I'm going to use IP tables to forward requests from port 80 to port 9000. What we really do not recommend is to run Play as the root user to get the server on port 80. That's pretty bad practice. Can result in some bad security vulnerabilities. And so don't run your Play server as root. Run it as a non-root user, which means that you can't listen on port 80. Then you use IP tables to forward. And then you can also set up front-end web servers that will proxy those requests as well. So things like Apache and Nginx are great at just fronting in front of your actual Play server. And the nice thing about this is that now these proxy servers, they can do content caching, they can do load balancing, they can make it so that you can have 2 instances that you can switch between and do that switch transparently, so when you do an upgrade, users don't have any downtime and that sort of thing. And then usually for applications that really need to scale, you're going to use a load balancer. And a load balancer, just plop it in front of your Play application and then send the request through the load balancer to your Play applications. Pretty simple to set up, things like the Amazon Elastic load balancers. Amazon and other cloud services also have a concept of auto scaling. You can set specific triggers that will add more servers to behind the load balancer, so it can be based on the number of requests that you're getting or how long requests are taking or all sorts of different metrics that will just add new instances behind the load balancer, and then all of a sudden you have more of those stateless web servers in Play that are all being able to handle your connections. So Let's talk about static assets for a couple minutes, and then we'll get to some questions. So Play is optimized for caching proxies, which means that Play is not really optimized for serving static assets in the most performant way possible. What it is optimized for is caching resources through proxies really well. So these proxies can be content delivery networks, which do edge caching of content. They can be those Apache and Nginx servers. And so Play has, out of the box, just an easy way to be able to change your routes from using using the Play server to handle the request, and instead using a CDN. So this is actually code from Typesafe.com where we do exactly this. What I'm doing is I'm saying if there's a configuration parameter content URL, then when I create the URLs to my static content, I'm going to just prepend that content URL. Otherwise, I'm just going to use the normal one. So this allows me to, in development mode, just have the Play server terminate the connections for the static assets, and then in production mode, I switch it over to the CDN. And the cool thing about this is that services like Amazon's CloudFront, you can actually set them up so that when a request comes into the CDN for a resource, if the CDN doesn't have it, then it then goes back to what they call the origin server, in my case, the Play server, to get that resource. And so this means that very few requests are going to be coming to the Play server for the static assets, but I still am able to bundle and have one thing that I create that is my whole application, including the static content. So that's really a great way to do that. And Play has the right request header handling in it to work with CDNs and caching proxies well. It does the 304 not modified stuff just out of the box. So last modified and etag just work out of the box. So also in Play, we can easily add asset fingerprinting. The reason why we want to do this is that when we have a request come in and we've changed some static content, we need to be able to tell the browser, hey, you need to fetch this new version. So this is the hacky way to do it. This is, again, code from typesafe.com. When the application starts up, I create a version stamp. This version stamp goes into the URLs for all of the static content. This is the hacky way because it means that every time we restart our Play server, we're going to have a new version stamp. Another easy way to do it is to have a configuration parameter that is your content version and use that instead of this auto-generated version stamp. So up to you how you do it, but essentially it's the same idea that you put into the path of your resource something unique that you can change the value of every time you change your static assets. This allows us to do far future expires, which allow for browser caches to be really aggressive about what they cache. So quick little example of this, if we go to typesafe.com and let's go check out the network tab here. So when we load this page, we'll see, actually let's do a control F5, which will load everything from scratch. We'll see that here's a resource here, main.min.css. See that this is coming from CloudFront, and we've got that fingerprinted part of the URL. And then we'll see some things in here like the response headers are saying we're setting the cache control far future expire, like, hey, never ask for this thing again. We're also giving it an e tag and a last modified. So now when I reload this page again, and let's go find that main.min.css, we'll see that now this time we still made the request. This time we got a 304 not modified because the browser said, hey, is this thing been modified since this e tag? And the Play server says, nope, hasn't been modified. Well, actually the CDN says it because the Play server said to do that. But then cool things like if we click on another page, then if we go look here, we'll see that this time it actually pulled that file from cache. F5 doesn't pull from cache, but just navigating through the site will. So see, we're taking full advantage of optimizing this application for all the static assets that get loaded in this application. So those are some best practices on optimizing the static asset part of Play. Let me give one quick little demo, and then we'll wrap up with some questions here. So we have a sample application in Play that's called the Comment Live Monitoring, and I'm going to come in here and run this thing. I've already compiled this for production mode, so let's go check out the application here. So localhost 9000. So what this application is it's a little demo to show us number of requests per second that the application is getting, how much memory it's usage, and how it's using, how much CPU it's using. And these values are getting pushed out to the client side from the server every 100 milliseconds using, in this case, we're using comment channel. So let's go actually simulate some load on this application. I'm just going to use Apache Bench and run a quick little load test on this, and we're really kind of handling up to once the JVM warms up to 3,000. Just kind of pop back and forth. Yeah, so one second. The moral of that story. Okay. No. Okay. So, anyways, you can try that on your own and see how great Play is at handling 30,000 requests per second in this case. But the really nice thing is that even while I was totally saturating this application with 30,000 requests per second, the cool thing is I was still at the same time pushing out new values for these charts every 100 milliseconds. So Play remained responsive while it was totally saturated with requests. And we'll see the memory usage is still up there. If we garbage collect it, then should come back down to meg heap. So there we go. So that is the presentation. I'm going to switch over now and look at some of the questions that have come in. And sorry, we don't have a whole lot of time for questions. If you are a Typesafe subscriber, then we're going to have a follow-up session in January that will be a lot more interactive. So let me go take a look at some of the questions that have come in. So there's a question about the monitoring tool that I mentioned, the Typesafe console. If you want to see a great demo of that in the context of ACTIVATOR, just go to the ACTIVATOR page on typesafe.com, and then there's a video there. You can watch the video, and in that video, I demo the Typesafe console. It'll show you all about that. So check that out. Let's see. Other questions that have come in. There's a question about using an external cache in Play. Caches, really what caches should be in Play is they should be things that make it so that I don't have to make a heavy query back to some backend data store, but I should always be able to recreate what's in the cache. And so if a request comes in and I can get the thing out of the cache, then great. If I can't get it out of the cache because it's either not there or because something is wrong with the backend cache, then I should always be able to go back to the backend data store and retrieve something out of the backend data store. So caches, you should never rely on them for always being there. There's one more question on the caching. There are a number of different caching plugins for Play. There's a default in-memory caching, and then there's go check out the plugins page in the Play documentation to see all the other caching plugins you can add in. And there's a question about deploying Play applications into servlet environments. Play does some really low-level networking stuff on top of Netty to be async and non-blocking and to be really highly scalable and performant. And so because of that, Play actually doesn't use the servlet API. It deploys standalone using the methods that I showed at the beginning to create zip files or create jar files for your application, and then you just copy those over to your server and start them up. So it's a pretty easy deployment model with Play, but it's definitely a different deployment model than the typical container approach. There's a question about what kind of security exploits might we be faced with? One of the nice things about Play's RESTful architecture is that we you can do REST service calls without using cookies. I have a blog on jamesward.com that goes into a lot of details, but when a request comes in with cookies, those cookies can open you up to cross-site request forgery attacks. And with RESTful services, we can actually totally avoid the use of cookies for authentication, which means that we can avoid one of the most common security exploits that web applications have. So so definitely take a look at my blog. Look for the article on securing REST services for more information on that. And there's a bunch more questions that have come in. Sorry I haven't had a chance to respond to all of them. What I will try to do is go through and respond to these via email. If you don't get a response from me in the next week or so, then send me an email, james.ward@typesafe.com, and love to help you out however we can. But I hope that was useful for you. The recording will be published on our YouTube channel in the next week. So thanks for attending, and see you on another webinar. Thanks.